Привет всем.
Hi everyone. So, I would like to introduce myself. I'm Sergey Prilutskiy. I work for MixBytes. Here is a bunch of presentations from auditors, and we also audit smart contracts. We have a lot of cool audits. Luckily, we did not breach anyone. We also do the research. We did a lot, like blockchain, lots of things we did. So we're interested about the zk topic. I will be speaking about SNARKs. It was a very good presentation from Sber, from Vladimir Popov. He spoke about what SNARKs are all about. Seems like that by the name of my presentation, people didn't get interested, but shouldn't do that. Seems like that you won't be able to find the names and how the companies will be exchanging the personal data, because they help us do what the state-of-the-art protocols, GVI tokens cannot do. The top universities do that, top cryptographers. It's the best topic in cryptography. Over the last 2 years, it went to prod, and these protocols are responsible for billions of dollars. It's a serious story, so I recommend you do that. I added something about SNARKs. It will be perpendicular. What is the zk-SNARK? Zero knowledge, non-directive arguments of knowledge, zero knowledge succinct non-interactive arguments of knowledge, zillions of algorithms based upon different primitives, which actually prove that they are arguments of knowledge. The argument knowledge. I know that there are some entry parameters that can lead to a certain output. They allow us to build systems that can do the calculations using secret data. So in SNARK, there are plenty of startups. In ML, there are plenty of startups that are required so that the neural networks operate using this data. They scale up the transactions. The dozens of thousands of transactions are wrapped in one proof. And what's important for safety is that they send these to trustless computers. So you may ask the computer to do some calculations, and it doesn't really matter who is going to be, whether it's an intruder or not an intruder. In blockchain, it's all strict. We can put a finger to anyone, to Vitaly Buterin, the system administrator, and say that he is breached. And if he is breached, it's good. But if it's not, then people don't do blockchain, as it were. So let's just find out what's the knowledge about why the name is so serious. Those who do blockchain, you may have read a lot of things about this. Here is the function that takes input and generates output, does not generate anything random. It is the deterministic calculation that is used there, and SNARK allows us to build this heuristic system that the verifier gets the result of this calculation without revealing the inputs, without saying which input data was used for that. In actual fact, the zero knowledge is written with small letters, not with block capitals, because it's a bonus feature. You can disclose the features. You can just put A in the power of billion, and I wouldn't want to measure the power of billion myself, but I would like to believe the final result. And the SNARKs help us identify the short cryptographic proof saying, okay, I buy it, and I can give it to anyone else. These algorithms actually started from supercomputers. When in a small computer, you just need to test and verify whether your computer made that calculation properly. That's where they started from, and they have a few superb properties. First, non-interactiveness. Well, initially these protocols were built like this. First of all, the tester sends a random challenge to the one who proves this, then it returns this to the inspector. So those were iterative protocols like SSL, SSH. It's all done iteratively. In blockchain, it does not work like this. In blockchain, you send the transaction hell knows where, someone processes it there, you cannot interact with it, you don't actually trust it. So you just need to do it in one go. And SNARKs allow us to do that. Here's the result, here's the proof, and it's verifiable. I already mentioned zero knowledge. If we build this function that you cannot identify output by that, you'll have this zero knowledge. It's a very simple example. In the schemes of verified credentials, it's used. So, for example, the hash functions, you know that I did not just take random bytes, but I know what this hash comes from. It's the quality of zero knowledge, and it's very important to mention that there is succinctness, compact proof. It shows that the verification of the proof in terms of its algorithm is much simpler than the actual proof. So I've done this calculation 1 billion times, and I tested this, and I've conducted this, and with that, I tested the proof. So it's the best system in terms of the effectiveness of verifiers, and they take it as one. So I gave it to the supercomputer, and I checked this proof for a second, regardless of the number of the cycles, whether they were 10 cycles, whether there was 1 billion cycles. This proof will work for the constant time. It's the best proof of the system, and they allow us to do so. They have some modifications. It costs some money, because to do proofs in this system costs a hell of a lot of money. And it's much easier to use a CPU for that, but still this thing works, and it saves people money. With L2 blockchains that are based upon SNARKs, the commission fee is many times lower than in the real blockchain. You may have heard about cryptocurrency mixers. It's all proved and proven by the attention paid to that by respected gentlemen. So this technology is very important, and this technology will live in the verified credentials world, where you will have to provide electronic documents. So this allows me to prove that I belong to a certain list, but I do not disclose who I am. It allows me to do anonymous voting, anonymously transfer the money, or prove that I have more than $100,000 on my bank account and I'm older than 18 years of age, but I don't disclose that, so I don't need to go to the bank to prove that. So these inputs do not leave the customer anyhow. So, for example, if we had a symmetric cryptography where the key was spread it where we have the two sides leaking the secret information. Then there was symmetric cryptography when only one side had the private key and secret information. Now we have the zero knowledge, third step, when no one possesses any secret information, but everyone can prove, and everyone can prove that. Everything is open, but the data is closed. Just do it. How is it done? Here's a very threatening-looking scheme I'm showing. So, as a framework, you'll use it as a framework. You may want to toy with that. It's a very good framework, and it's very nicely fitting these new targets. You can use these SNARKs easily. There are many proof systems for that. So, for example, you've created a calculating function when it transfers to the arithmetic circuit. So this very much looks like a printed circuit board, which looks like a number of gates. So the signals go through different arithmetic gates, and the gates emitters go to the collectors of other gates, and they close somewhere in the register, and we get the output after the verifier. So we get this linear approach. So it seems like we have done it in one go. This circuit board, this circuit generates two pieces of data, proving and verifying key, proving key and verifying key. They're called key. I don't know why, because we think that key is something secret. Now the keys are public. So, for example, you use GitHub with this circuit, you publish this, you run this setup, and you show to the entire world. You would like to prove them and verify that. Proven key is more. The longer number, the verifier key is smaller, because in blockchain they very much like to put the verifier in smart contracts. They don't have much space, so their blockchains are loved by SNARKs because we can do a lot here, and we just send a tiny little there and prove that everything is good. It's the first part of the setup. We touched upon this function, we generated the keys. And what's happening next with the prover? The prover takes the keys at the fourth step and puts them through this arithmetic circuit, and we will mention that. It's called a witness. In the assignment table, you'll be able to see this, and maybe you took a picture of this circuit and you wrote the values in the chart as a name of each output, as a name of each gate. So you've written all of these values, and you've created a file with the intermediary values. Of course, it's expensive, but for the sake of some tasks, it's worth it. Then this witness is put in the prover, and Vladimir actually told this story, how this witness is turned into a pack of polynômes and great powers, so they can create commitments. When I say that here is a verifier, here is the verifying commitment, I can prove that my secret polynôme in the secret point, and I can calculate that, and I can verify this. And it turns into a system of equations. I can simplify this, of course, and here's the output and the cryptographic evidence. And then there is verification. We put verification and proof to the tester. The tester takes the verifying key. In the best protocols, it's dozens and dozens of kilobytes on the elliptic curve. they launch the verification of the proof. It's not a very easy task to follow because it runs the calculation with lots and lots of bits on different elliptic curves. There are pairings on elliptic curves. So it's a very complicated and complex calculation, but in best systems, it's constant. It runs in a constant time or logarithmic time, which is also great. And the output of the verifier is true-false. Either it accepts this verifier or not. And you can put in very massive programs there, like virtual machines these days, Ethereum virtual machines with transactions, with some input data, like the fulfillment of the smart contract in the virtual machine, with SNARKs that prove that the correct fulfillment of code, the code was run correctly. It's not just the proof of any single one, but it's the proof of the work of the virtual machine. It's a great thing. And there is a RISC-0 project already. It may be somewhere on the side because they would like to use some different encryption, which can also prove it with the set of the RISC processor's instructions. It's a great story. But anyway, we were going to speak about vulnerabilities. So I took some articles like threat model.
Если посмотреть на вот эту
So if we take a look at this chart, you will see that there are just two crosses there. These crosses are things that you know, someone does not know, and someone does not know the private input and private witness. Elsewhere, maybe no, maybe not. But we are in blockchain, so we believe by default that everyone knows everything. Input and witness don't know, all the rest know everything. And here we have the intermediary services that help you in the cloud to do the proving, to prove it. Because you cannot do it on your own PC, on your own computer, because it's a hell of a lot of a task. And you'll have to wait too long before something is proven. So you'd better use the cloud. Now we just consider the vulnerabilities. So I'll skip to the next slide. This is what the hello world looks like in CIRCOM. Factor 1, input number 1, factor 2, signal factor 2, and we have val signal. It's made of one arithmetic gate, and it multiplies them. In the final component, we have less equal with the reproving. The fact should be changed that from that gate we have the multiplication of these two numbers. So we do not write the code of the function, we just write the specification of the circuit board which does this calculation. So it's just rather a language of macros or technical language. We describe our arithmetic contour, which number goes where. This is our hello world in this language. So where can we have some problems? What can go wrong here? So the first example, when the programmer somehow does not create a constraint. Constraint is yet another equation is added to the system of equations which will prove that everything was done correctly in that particular area. There are lines that highlighted in red, like smaller minus minus. It says it's taking the signal value and you just squeeze it in the output signal through the gate. You should not put any constraints here. You should not come up with any constraints. You should not prove that everything works correctly here. It just proves that the attacker can take the witness and with the inv, the INV, they can put any value. They can take that INV and change this and generate the proof, and it will be proven correctly because there is no condition to prove it.
Ну,
Sometimes this happens.
как бы темплейты все как бы покрыты констрейнтами, но иногда
These templates are covered by constraints.
То есть в данном случае как бы здесь
In this particular case,
потому что
inv is used because the overflow is possible. So these mathematical operations are all overfilled. It's a standard story because all of the operations are done by the module, by the group order. So you can add two numbers and get a sum less than 2. So when the bytes were overflown and ints were overflown, but in Stark the hundreds of bits numbers are overflown depending on crypto fields. So here it's done just to prevent the overflow. So it seems like the attacker, even if they write anything into that INV, the last line, the last string will eat him. And it's done so that in this ternary operator, under the bonnet, there is a compiler with a few constraints to make sure that there are fewer constraints, at least by one, because here are the number of constraints. Like, for example, less, minus, equal. There may be gigabytes of those. So, in other words, the approving will be very hard and heavy. But it's a rare thing that we see here. These are the bugs related to optimization. The next story is when we write the constraint, we believe in it, but we forget about how mathematics works in secrets. And here's our hello world. I prove to someone that I know two numbers that will give they will give this result. It's a trivial task, but if you take a simpler task, it will look even more interesting.
В данном случае мы можем просто забыть о том, что доказывающий зловредный, как бы, который хочет, как бы,
валидный proof, see that it's the intruder who can generate these numbers, and they can put the number of 1 and the number.
А если этот кусочек используется, например,
if it's used,
того, что комиссия какая-то вычисляется, там,
if there is a commission,
не знаю, проценты какие-то этим умножением,
commission fee calculated. The attacks are possible here, but Starks very often prove that from one balance, a certain number of tokens have been withdrawn and a certain commission fee was charged. So the cost for that error will be very high. Additionally, you need to check and verify this with zeros so that there is no overflow. In the normal world, in the normal environment, APIs operate with normal numbers, and here we just overcome a great number like 0 and the number as large as a group order are the same. Well, in terms of maths, it's the same inside the circuit. Here's this next story.
Грубо говоря, вы генерируете proof.
So if you generate a proof for some logic, and if you have the input signal, for example, if you prove that today I will give this number, and if it's hashed, previously it had been added to a Merkle tree, and depending on that, I will be able to pick up my deposit. This is how mixers work, Tornado Cache, for instance. There may be input signals that they are not involved in logic. Smart contracts are in process because smart contract checks the proof and it says, you had a deposit, I will give you the money, I will send this money to such and such address, but this address, the recipient was not involved in any logic. logic.
атакующий может перехватить.
The attacker may intercept somebody else's
В этой транзакции
transaction,
будет валидный zero
and
knowledge
this
proof,
transaction will have a valid zero knowledge proof,
но он сможет подставить свои собственные
but they may put their own values.
Все фронтрайнс вообще
And in
как бы все
blockchains,
и можно без проблем.
everything can be intercepted easily, can be used easily.
Обязательно быть
So
привязанным
the
к
input
этому
values
пруфу. Вот для этого
should be linked to that
то есть
proof.
все, что попадает на вход, оно должно
Everything which is in the input
ну, в данном
must be
случае
processed inside the circuit.
потому что я не знаю, как
So
сейчас.
here they are put in the power of 2.
Напишите входной сигнал там такой.
Previously, if you just put this
Компилятор видит, что с ним
entry signal such and such, the compiler sees that nothing happens to that, and it will be thrown away from constraints. But if you multiply this, they will gate it, they will check this and verify, and this proof remains valid only in this case. So everything which goes there with proof in smart contracts should be wrapped in proof, at least formally. The next story, when we, of course, take this circuits packaged, just like in the circuit boards, a big circuit board with a chip, a multiplexer being one of them. Another one is the multiplier. Here we compose them just like on a circuit board. There are plenty of components of which I will speak. A programmer, for example, in this particular case, uses the component which helps and verify that one number is less than the other. In Stark, it's a very difficult operation, and it's very difficult to identify which number is more and which number is less. In bits, it's very difficult to do, because we work in the field.
У вас там, грубо говоря, одно число.
For example, roughly speaking, one number module-wise is more, but in actual fact it's less. So in the circuits, you just need to split this number into bits and compare these bits before we find the difference. Whose bit is older, he is the winner. So here's the circuit that compares the two numbers, and if this output is unused, the programmer may think, okay, I've just put two numbers there, one should be less than the other, so he did not use the inputs, but the intruder, the attacker, may throw in the values which will not pass the range check. Here is this link to the bug which was identified, and it was related to that. So it's a must that we use it. Down there is a fix shown, a strange looking one, but everything looks strange. In SNARKs, it checks and verifies that all of the 10 components of big less than returns 1. But R should be constrained to 10. It basically means that each of these 10 outputs returns 1. Otherwise, everything crashes. And there was a bug detected.
Опять же, про overflows, еще как бы...
A few more words about overflows. Overflow really rules. Overflow rules, it's a standard story. It does not just process. It could not be processed here because all of the elliptic curves are overflow. They are constant overflow, where these elliptic points are positioned. So here's the overflow.
Любые операции с какими-то числами из реальной жизни.
So any operations with the numbers from the real life, like, for example, hash, electronic signature that come from cryptography. But if you speak about percent, sums, amounts from the real life, they require range checks. For example, check that we have received a sum less than $1 million and not zillions of dollars. So range checks are mandatory, they should be there. They are hated because they are very, very difficult. So in order to run a range check, you just need to split the number into bits and make sure that the older bit is not exceeding a certain value. So you need just to do this crap, and it really reduces the efficiency of circuits, because if you take a look, if in the normal circuit board a bit runs through a connection, here is the 265-bit number runs, and you just take 256 bits and you just turn 256 bits and 256 conductors. It's not effective. It's tedious and people hate it, but we have to do it. There are special circuits that split the number num to bits and bits to num, and they're used very frequently, and as a parameter they take lin u. So it depends on how many bits they should be splitted. So they should be split. You can take a byte of something, you can lose something. So the range check may malfunction. So you can send a certain number which will be bitten, it will go through range check, but it will be more than the required value. So that's what has to be verified. Another story which is related to the interaction of your business logic and proof. The mathematics in circuits is the same. It has its own margins. There is a certain type of overflow, but in Solidity there is a different type of overflow. 256 bits overflown with different margins, with different margin size. So you just need to take a look at these cases differently when there is something running bad. Nothing that breaks circuit breaks Solidity and vice versa.
Ну, то есть у меня такое вообще дежавю, что я возвращаюсь.
I actually experience a deja vu, like I'm going back to the 90s, when you would have to take a look at each and every byte so that it does not exceed the number of 255. Here are just more bits, but you just need to take a closer look at that, and you just need to save each and every constraint. Like I was saying, if you send the wrong size of these bits, can play very, very bad joke on you. Just like in Web 2. Here is the situation when there are two circuits giving you two sets of bits, and you glue them together. Maybe the programmers decided that there is a miracle, and they've taken just one half of the hash, and the second half of the hash was written to second part. They feed it to a circuit, and something should be bitten there. So these collisions should also be tracked and monitored. In actual fact, you save constraints here, because when you write such proof, you see it works for an hour. You just sit there and wait. I guess the user will not be waiting there for an hour. And of course, on a mobile phone, they will be waiting for 1 year. What about this 256 bits? Let me just byte it to 128 bits. So you byte it, but there's different type of security. As we work in the field, the security bits is not just like in the simple symmetric cryptography. The value is smaller, the bits are smaller, so you just need to track this.
Не любят в снарках все наши стандартные алгоритмы. SHA-3, SHA-2.
They hate standard algorithms. Key checks, IS, all those popular ones, elliptic curves, because they work here really lousy. Symmetric cryptography hates this, standard curves hate that, because they don't have too many optimal snarks. So with snarks, they've got their own crypto algorithms that work really nicely, like the Patterson hashing, Poseidon, MIMC, all those things that are shown in Starks. There's hashing, which is 1,000 times much more efficient. They're especially targeted for snarks. There are no serious bits operations, and they work on snarks much more rapidly. But they all have their own subtleties, these algorithms. They have different crypto resistance. They have different types of bits. The Patterson hashing is used here. Patterson hashing, it gives us out 100,000 constraints. So we take Patterson and it gives us hundreds, 500,000. So the difference is huge. There are not too many bits operations, so it gives us a point on the elliptic curve Patterson, but it suffers from their own problems. For example, they've got collisions so that they can input different lengths of bits. So you just need to feed the data from one set of bits. It's good, but when you start moving it, everything is going to be bad. So they put the point on the elliptic curve, and these points are in symmetry. So if x, y, x minus y are symmetric, if the programmer uses the x of Patterson hashing, we have the natural collision there. So we can show another point. So Patterson hashing is homomorphic property. We can multiply two Patterson hashes and we get the hash of the sum. It's a cool story for anonymous voting. So homomorphic property is a separate topic in cryptography. It's a great one. But in terms of security, if you see such a hash, if it's used a number of times, you just need to remember about homomorphic property. If that's a secret, we just measure it easily, which is of course unrealistic for the real symmetric algorithms. So here we have Merkle trees. Merkle trees are the most popular proofs in SNARKs. You can use this for showing your passports, anonymous transactions.
Они здесь обычно используются такие кастомизированные.
They're used here as customized ones, so that we can include
для того, чтобы можно было
it in the Merkle tree, so that we can optimize the storage of this Merkle tree in smart contracts. There are plenty of them, and the Merkle trees have their own problems. For example, the most trivial story here is that we have a sparse Merkle tree.
Там большинство листов, они как бы пустые.
With most of the leaves being empty, they're filled with zeros. When we add a value to the tree, you can simply replace one of the zeros by that value. We include this value there, but by excluding, we add a zero. So we do this exclusion proof. I can prove that I do not belong to that list. And I prove that instead of my hash, there is a zero in place. Therefore, there was not a zero, now there is a zero. I published these two types of proof, and I proved that I deleted myself from that tree.
Там для оптимизации часть этого дерева, которое
to optimize part of the tree on the right hand side, it's filled up with the zero hashes till it reaches the root, 0, 0, 0 till it reaches the root. There may be not zeros by constants, but pre-calculated. So these constants may be passed there, saying that I'm in the tree. It's a strange bug, but it was found there. Instead of using hashing and overflows in risk, you can find some overflows here. But also there is an attack on Merkle trees. It's called a second preimage attack, when you take the intermediate node as a leaf, not a leaf down there, but you take an intermediate node as a leaf, and you just say that that's a list, you claim that's a list, and of course you can make this Merkle proof out of that. You may be aware of the hash, and you cannot create this proof, but you can create this proof by the a known leaf of the tree.
То, про что надо читать, если вы...
So this is what you need to read if you specialize in Merkle trees.
Бизнес, как бы мы предъявляем
Now,
input
for business, we provide this proof parameters,
как бы
whether the proof is correct one,
работа с нулифайером,
and
то есть когда какие-то одноразовые значения в контрактах очень любят, чтобы ты мог потратить, грубо говоря, свой листик в Merkle дереве один и только один раз.
in Merkle trees, so that you can spend your leaf in the Merkle tree just once and you cannot repeat it. There are different types of attacks that utilize a few nullifiers, as they are called, nullifiers, non-deterministic nullifiers. It's not recommended to show any values in smart contracts unless they are hashes. Even if they are shown just once, if it's a secret input, you committed it once and you show it for the second time. And for the third time, you won't be able to use it. Seems like that you can send open values, but it's best that you send hashes from that and you do not disclose this signal, because this will later forbid you to use it the second time. As far as range checks are concerned, there's always overflow everywhere. So some people would say that in the new versions of Solidity, any overflows crash. Well, in terms of the auditor, the controlled overflow is just the same vulnerability, which may actually freeze the protocol completely. It's also a critical vulnerability. And of course, the business logic is obvious. Now there is some implementation of proof systems, systems that generate the keys. For example, this next presentation will be a hardcore one. It's related to the frozen heart attack. It's the attack about the Fiat-Shamir heuristics.
Сколько там этих уязвимостей внутри, как
and how many vulnerabilities
потому что они все супер молодые, постоянно как бы.
We don't know.
Вот, но я повторяю, как бы в проде уже это работает, и люди, в общем, доверяют.
In prod it already works.
Деньги, так что тут все говорит само за себя.
It's serious money, so everything speaks for itself. The verification of the setup procedure, there may be different ones. There is a trusted setup, there is a transparent setup. It's a standalone topic for a separate presentation.
Объем полей, как бы, и битность используемых алгоритмов.
The weak margins and bits used. Not all of the elliptic curves are considered to be super secure, but they are secure, and the implementation of arithmetic is also very, very serious. And now the mitigation.
Такие как бы чек-листы, ну, они уже, в общем-то, есть, как бы, но так, если резюмируя.
If we make a summary out of it, any input should be constrained, any output should be constrained, and any output of intermediate circuit is always constrained. Every input, if it's not involved in the logic should be put in circuit. Any input which does not relate to cryptography should be covered with range checks. Do not utilize any data with different lengths of bits. Everything should be, you know, fixed. We use safe Merkle trees so that the leaf and the node would have the different size, the different length. Then we mitigate this attack.
И даже если вы кастомное дерево используете каким-то...
Even if you use the custom tree and you fill it up with some additional values, like with indexes, and they are made with few of them, you can apply range checks. Do not disclose nullifiers, even if they are not used for the second time. Do not disclose them, do not open them.
именно хэш от своего секретного нулифайера.
So you just need to say that you only open the hash hash from your nullifier. You use the secret functions. You need to read the papers about them. You check and verify their properties and why they may turn out to be bad. Also remember about malleability, and you may generate a valid signature, malleable signature, and it also relates to SMARK proof, and it relates to some SNARK proof systems. You can take SMARK proof and make it valid. It will remain valid, but you will change the bytes. Basically, there is a lot of things to mention, so welcome to join us in this brave new world. Please join us and study more. Thank you very much.
Устойчивый ли текущий zk-SNARK к атакам
Is zk-SNARK resistant to the attacks with the use of quantum computers?
Неустойчиво к атакам.
Everything with the quantum curves is not resistant to the quantum computers test. Everything which surrounds us is not resistant to the attacks of quantum computers. All of the passes, plastic banking cards, they use elliptic signatures because they are quick and simple, so everything which is based on them is not resistant. But quantum resistible SNARKs do exist because there are things which do not use elliptic curves. They have less effective verifiers, but they have other advantages. Like, for example, they have a transparent setup, without any hidden tricks, but it's going to cost us more to verify the proof. People from Web 2 don't care much about it. Those who specialize in smart contracts, if they have verifiers in smart contracts, they need to have those. But we have more processing power, we can do it much more easily. So, of course, it's not tolerant to that, it's not resistant to that, but what not? Other SNARKs different from singular curves. There are SNARKs made up of two parts. So one part is the arithmetic part, when we turn our code into this arithmetic circuit. And they can be made in different ways. There can be different types of gates. There can be optimization of different logical operations like ink sort with tables. That's one part of SNARKs. And the next part are the commitments, that the polynomial was evaluated in a certain necessary point. There are two things. If you take a look at all of the algorithms, you just take a whole big tree, but there is a lot of commitments which is built upon favorite hash functions on the correction codes, and these algorithms are resistant to the quantum computers, and they do not use elliptic curves. And these schemes are the most popular ones because they make provers easy. The proving,
то есть вам нужно еще как бы сделать n log n, как бы...
You need to do n log n.
Это не очень хорошо, как бы лучше сделать на прувере O от n и
You'd better do it from n,
как бы на верификаторе. Вот сейчас вот лучшая схема, они
use the verifier for that. So the best thing is to use this particular approach. That's what people try to use for virtual machines that try to do the risk extraction set, EVM. They are the most popular schemes. Another thing is the recursive SNARK. When you do the proof that you have checked and verified another proof from another system, that's where you can check and verify that. And there are a lot more. But here it's just like an avalanche of the new articles, and people work on that, so wait and you'll see more of them added.